All right. Good morning, everybody. So previously we talked about the differential equation dy dt equal to some proportionality constant times y, and that comes from, or that is very often the differential equation that describes a population represented by T, the population size, the number of individuals in my population, be it bacteria or fruit flies or people at a certain time, and the population grows at a rate that is proportional to its size at that time. And I get this differential equation. That is a mathematical translation of this second sentence. I also want to know how many I have in my population originally, my initial population size, and between the two we can solve that differential equation and find the function that describes how the population excuse me, how the population grows. And we found that, let me just copy the differential equation over here with my initial condition. This together, after a few steps, we get our exponential growth function, initial population size times e to the kt. So it's important to note here that k is positive. K is called the growth constant. But so there's also another side to this. When K is negative, often if we look at radioactive material, various radioactive substances, there the substance decays, becomes less at a rate that is also proportional to the amount left at that time. So if we now let the y variable represent the amount of the radioactive substance left at time t, then again we are going to have a differential equation where the rate of change, the decay rate in this case, is proportional to the amount left by some proportionality constant. And again, I want to know how much there is the initial amount. Now my k is going to be negative, and k is called, in this case, when I'm talking about an amount decreasing, the decay constant. But I have a very similar situation to what I've had before. It's the same differential equation in appearance, it's just that the k constant is now a negative number. So how I'm going to solve this isn't going to change because the differential equation looks exactly the same. So it's the same sort of template solution of an exponential function, but k is now negative. For example, k could be negative 0.01. Let me make that negative much clearer. Negative 0.01, for example. So what happens when I visualize this? And how does it relate to the exponential growth? Well, exponential growth had a positive exponent here, resulting in the following graph. I have my time, I have my exponential growth, my y value. I start at an initial amount and it grows exponentially. Decay, when I have a negative exponent, it's going to reflect it in the vertical axis. And it's essentially going to be the other half of the exponential graph decaying down to my horizontal asymptote, at y equals 0. So radioactive decay, according to this model, the radioactive substance never completely goes away. It just approaches 0, but in theory never gets there. So let's look at some examples to see how this is going to look in a practical problem. So the first one I want to do is 1430. And let's read it. 500 grams of iodine 131 is decaying at a rate proportional to the amount left at that time. That's a key sentence that gives us our differential equation. After 3 days, 386 grams of iodine 131 is left. Solve the appropriate differential equation to find a function giving the number of grams of iodine 131 and determine how much would be left after 2 days. Well, one thing at a time. We have to define our variables first. Let y represent the amount of Of course, we're talking about iodine 131. We don't have to be too detailed in our sentence. The amount left at time t, and it seems like time is in days this time. Then the sentence is decaying at a rate proportional to the amount left at that time is allowing us to translate that to our familiar differential equation with 500 grams originally. Amount in grams, not that we're obsessed with units, but it's good to be aware. Now, we've done this a few times in the interest of saving time. It's always the same process. I'll do it once and then we just need to be aware that we may need to be ready to solve the differential equation as our first part to an answer, but it's always the same. So after a while, you get used to the process. The actual value of k is irrelevant in the solution process. I separate the variables, I integrate both sides, I get a natural log, kt with the integration constant. Then I solve for y, and I write to a more convenient integration constant. instead of e to the c. Then I use my initial condition to find that if I plug in 500 for y, e to the k times 0 is 1, so m is 500, and therefore my function is 500 e to the kt, big surprise. We've seen this before, it's always the same if I start with the same differential equation, which I do. So now I need to know what is k, the decay constant. And that's why they give me this other bit of information. They tell me, in addition to the 500 I start with, that after 3 days, 386 grams will be left. So after 3 days, so I have some extra information that at 3 days, I have 386 down from 500. So I can use that and say that, well, 386 has to then equal 500 e to the k times 3. So e to the 3k is 386 over 500. 3k is therefore the natural log of that. And so k is a third of log 386 over 500. And let's see what we get for our k. I get negative 0.086. So negative because the rate of change is negative. Remember the rate of change is k times y. Y is always a positive number. So if I'm going to go down, if I'm going to decrease, then the k has to be negative to make the derivative negative. So that is all making sense. And there's my k value that I can use in my function whenever I need to. So it's very similar to what we did yesterday. It's just that negative k values correspond to things that are decreasing in this exponential way. Then they ask, determine how much would be left after 2 days. All right. So after 2 days, that is going to be y of 2. I plug it into my function. I have k if I need it. So I can calculate this. Let's do that. And we get that 420.77 grams were left. You can write your concluding sentence here. We had, I guess, approximately 420.77 grams left. So everything is very similar. We just now have a decay scenario, and the decay constant instead of the growth constant is the only real adjustment. So last time we talked about doubling time, the time it takes for the population to double in size. Here we have a similar concept, but it's now backwards in a sense. It's called the half-life. So what we have is the half-life is the time, let's call it tau, that it takes for the radioactive substance or whatever we're looking at to decrease to half of what it was. That means that after this tau time period, which we call the half-life, I have a half of what I originally had. Now I know what this is. It's y0 e to the kt. Well, now tau equals 1/2 y0. So you see again, it was independent of independent of the initial amount. It didn't matter how much I had. It's all proportional, half of whatever I had. So I have k times tau equal to natural log of a half. So tau equals natural log of a half over k. So visually what that means is the following. Very similar to what we did yesterday, I'm just going to start with some initial amount, and it's going to decay to get to half of what I started with. It's going to take some time period, which we'll call the half-life tau. From this point, to get to half of what I had at that point, which would then be a quarter y0, takes another tau, and so on and so on. So the half-life is another way of indicating how this decay process is happening. It's not connected to how much I have, but rather a proportional decrease from whatever I have relative to the amount that I had. So let's see that last bit of the question. Find the half-life of iodine-131. Now you see here in our example, we can now continue this for our radioactive substance. It'll be log of a half over our negative 0.086 and so on. So let's calculate that. I want to use enough of my k value so that when I round to a couple of decimals, I am still accurate. And we get, in this case, 8.04. So this will be days. So approximately every 8 days, is not perfect, we lose half of the radioactive substance. On day 16-ish, we're going to be down to a half of a half. And then on day 24, we're going to be down another half and so on. Never actually getting to zero, but it is decreasing quite rapidly. All right. I'm trying to get through enough questions to see all the variations. And we can always rewatch the video if it feels a little fast. I want to get to 27 here. Let me do it this way. That's better. Okay. 1427. A large cloud of radioactive debris from a nuclear explosion has floated over the Pacific Northwest, contaminating much of the haze supply, or contaminating much of the haze supply. Consequently, farmers in the area are concerned that the cows will give contaminated milk. The percentage of the initial amount of radioactive iodine still present in the hay after T days is now represented by P of T. So they define it for me. I don't have to. It's not a Y. It's not an N. It's a P. And it decays at a rate proportional to the percentage itself, with a decay constant of negative zero point 0.1. All right. So that allows me to set up my differential equation as a translation of that information. Oops, not Y. Haha. My initial percentage, do they tell me that? I don't think they do at all, do they? Let me just triple check here. They're concerned about the cows giving contaminated milk. They define P for me. It decays at a rate proportional to the percentage itself with a decay constant of negative zero point 0.1. Now it's a little bit deceptive here because now the amount is as a percentage that at the start there's 100% of the radioactive substance and then it starts decaying. So I'm going to start here with 100. Now my differential equation is always the same regardless of the name of the variable. So I'm going to go about my business and solve this the exact same way, separating the variables, keeping the constant on the right, integrate both sides, natural log of p in this case, negative 0.01 t plus a constant. So p is then e to the negative 0.01 t plus a constant, or I'm going to rewrite that as m for a more convenient integration constant. Then I'm going to use the fact that I start with 100%. It hasn't decayed yet at the start. So 100 equals m times e to the negative 0.01 times 0. It becomes tedious to write this out perhaps, but with this I'm practicing that first part of the question that is going to ask me to confirm what the differential equation is and how to solve it. How do I get to this function that I will use from now on? So I know what my target function is, and in this case I have k, I have everything. It's a question of do I understand how that is obtained? Where that comes from? Why? All right, now that I have my function, which is a very familiar looking function, I'm just using a p instead. 1 and 2 are very much the same question. Find the percent remaining after 4 days and 10 days. So I just want to see, let's say 1 after 4 days, we have P of 4. I plug it in, I get a number. The 10-day one is exactly the same, except I plug in 10. So 10. So let's do that. Do not skip anything. So for the first one, I get 96.08, and the unit here is percent. And for the other one, we get 90.48%. All right, so basic, plug in a time value and get how the amount has changed. That is definitely the most basic kind of question. Let's see what else they have here. So we've done that. Number 3, some scientists feel that the hay is safe after the percent has declined to 10% of its original amount. So now P is 10. Find a number of days before that hay may be used. So now I want to know in number 3, when is P equal to 10? Well, that is going to be when I plug in 10 for P and I solve for T. So E to the negative 0.01 T is therefore 10 over 100 or 0.1. So negative 0.01 T is the natural log of 0.1. So T is natural log of 0.1 over negative 0.01. Let's see when that happens. And we get 230.26, let's say. So T is in days, right? So if they are aiming for safe milk at 10% of the radioactive substance, or the radioactive substance decreased to 10% of its original amount, then it'll take around 230 days. However, other scientists, let's move this to the top, other scientists believe that it's not safe until the level of radioactive iodine has declined to only 1% of the original level. Find the number of days that this would take. So now I'm going to do exactly the same, except ask the question, when is my P value 1? So that's going to be when I plug in 1 for P and solve for T. So e to the negative 0.01 T is then 1 over 100, which I can simplify to 0.01. So negative 0.01 T is natural log of 0.01. I can't cancel these 0.01s. This second one is in the function, in the log function. So T is log of 0.01 over negative 0.01. So let's see what that is. Actually, I can just go and redo that one, can't I? Like so. Whoopsie. Now where's my answer? 460.52, let's say. So it'll take 460 days, so a year and a bit, a year and a third-ish, to get the hay and therefore the milk down to a safe level, depending on what they consider to be safe. So we see here the same kind of thing happens. I start with my differential equation. Solution's always pretty much the same. I just have to be able to verify that. And then once I have the function, I answer a variety of questions, sometimes plug in the t value, sometimes having a function value and finding the t value, but it all comes from that function. All right. So it's familiar, but the wording and the setting is different. Now, I will say at this stage that there are more questions in this problem book, Newton's law of cooling, fish population, and mountain goats, and all kinds of stuff that we won't be covering right now. I want to go to number 20. So for now, we're only focusing on basic exponential population growth and radioactive decay. I want to do 20 and 21, and then we are done. 1420, half-life. If 10% of a radioactive substance remains after 1 year, find its half-life. Now, there could be some more words here, admittedly. We are only looking at the situation where the radioactive substance decays at a rate proportional to how much there was. So we are always going to work with the same kind of differential equation when it comes to radioactive decay. So let's set that up. So we have to define maybe a y again. Let y represent the amount left at time t. Do they give a time unit for me? Year, yes. Years. Now, I am always going to have the information that I translate to my differential equation, which is some decay constant times my function. Then we go about our business. Oh, we need an initial amount, right? We don't know that either. 10% of a radioactive substance remains after 1 year. They don't tell me anything, so I have to leave that general as well. So from this, just like before, like the very first one we did, you can go through the motions, be sure you can do it, and we will of course get the familiar exponential growth decay function. So now they give me the information that 10% of the radioactive substance remains after 1 year. So extra information. After 1 year, we have 10% of the initial amount. So that then goes in here for 0.1 y0 equals y0 e to the kt. No, not t. T is 1. Time is 1. And you see here, they didn't give me the initial amount because it didn't matter in this equation. So e to the k times 1, so just k is 0.1. So k is simply natural log of 0.1 with no extra calculation. I get negative 2.30 if I round to 2 decimal places. So now I have my k value that I can put in there in my function whenever I need to. Actually, let's just check the question. They don't give me everything, so I can't answer all kinds of questions. I have K, and I'm looking for the half-life of this radioactive substance. So I can do that. So now half-life, that we will call tau, is log of 1/2 over K, and I can then calculate that as follows. Half-life is pretty short, 0.30. That'll be in years. So just under a third of a year for this substance. So it decays quite rapidly in comparison to other radioactive substances. So even in a question like this, where they don't give me much, sure, there should be more words so I can set up the differential equation. I don't know the initial amount, so I can't answer everything, but I can certainly do something with this question. Try to get to this last one, and then we've covered pretty much everything. 1421. Carbon-14 has a half-life of approximately 5,730 years. That's longer. This means that after 5,730 years, a sample of carbon-14, which is a radioactive isotope of carbon, has lost 1/2 of its original radioactivity. That's what half-life means. So it just takes a very long time. So it's very stable. Estimate how long it takes for the sample to fall to roughly 0.001 of its original level of radioactivity. So now, by giving me the half-life, in order for me to answer this question, I'm just going to do it short so we run out of time, so we don't run out of time. Y is still going to represent the amount of carbon-14 left, and so on. T is in years, just like before. So we're going to get the same equation, same function, some initial amount, e to the kt. Now they give me the half-life in this equation. This is 5730. But then I can always find k from the half-life and the half-life from k. If I have one, I have the other one. So I can very easily find k from this information by just solving for k in the half-life equation. I can easily find the value of k. Let's see what that looks like. Now for these situations, k is quite small, 0.00012 and so on. So if you have a normal calculator, you can put that in your memory and all kinds of stuff to make sure you're working with the most accurate k value in the future. So now if I have the k, I can better answer their first question because I now have things I need in my function. So by them giving me half-life, they are essentially giving me k. This is just a nicer looking number than the actual decay constant. How long would it take for a sample to fall to roughly 0.001 of its original level? So now for number 1, we're looking to find, we want to find t when my function is 0.001 of its original amount. So that means 0.001 of y0 is y0 e to the k t. And I know I have t. Sorry, I want t. I have k. And again, I see I don't need the initial amount. E to the kt is 0.001. And we see these things sort of repeat themselves over and over in the kinds of calculations I have. Natural log 0.001. I'm looking for t, so I divide both sides by k, and I have k if I need it. Put it in your memory, do whatever you need to do. I will try and use the most accurate k I can. And we get 57103.94. So that is roughly 57,000. So that's roughly 57,000 years for carbon-14 to decay to about 0.1% of its original amount. So it takes a really, really long time. Let's make a new page for this last bit. And again, just trying to squeeze everything in so there are no surprises really for the kinds of questions. Let us see. Where's the question? Okay, so here we go. And oopsie, let me just go back. There we go. Number 2. An old sample is discovered and found to contain 40% of the carbon-14 when compared to a similar current sample. How old is the discovered sample approximately? So this is called carbon dating. By measuring the carbon-14 in an old fossil or something and comparing it to what I found in current comparable samples, I can get an estimate of how old that sample approximately is. So I get an old sample and I see, oh, there's only 40% of the expected carbon-14 left. How old is that sample? So how long did it take for carbon-14 to decay to 40% of whatever original amount there might have been? So in number 2, we're looking to find the time that it takes for my carbon-14 decay amount to be 40% of what it originally was. And I don't need to know how much it was because this function that I then plug in is going to have some initial amount, e to the kt, and I know k. And again, I see the y0s cancel. I don't need to know how much exactly there was. It's all relative. So I have 0.4. So same process, kt is the natural log of 0.4. So t is natural log of 0.4 over k. And I just have to make sure I use the most accurate k I can coming from the half-life formula. So what do I get here? I get the same number. That doesn't, did I do something wrong? Let me just do it again for safety. by K. I'll use the formula. There we go. 7574.65. So I could say the sample is approximately 7,574.65 years old. So even with this basic differential equation, there is a lot of interesting things and very practically relevant things one can do, like carbon dating and things like that. All right, we will end it there for now. That gives us a good variety of questions for um, radioactive, basic radioactive decay questions.